Okay, so we're ready to go for the main lecture for today. And so the point of today is the center of k-space. So the center of k-space has kind of like a special effect. The center of k-space is actually the center of the echo. Center of echo. So we're always talking about, what was the amplitude at the center of the echo. So it turns out the center of k-space is the center of the echo, and it has a very strong effect on what the image looks like. And so what we want to do is today is sort of go over, what is the center of k-space? What does it actually represent? Just using our very simple cosine brain again. And then we'll talk about a complex image. And so this is basically, it took me years to finally get here, but this is what you get from one point in k-space. You get a complex image that has an imaginary part of it. And so what does that mean? It turns out that this complex image is very similar, it's virtually identical to what a gradient does. And so this will sort of be one way of sort of figuring out what a gradient does to the image. So one complex image that corresponds to one point in k-space actually looks very much like what a gradient does. And that's not surprisingly, because we turn the gradient on, record a bunch of points, each one is like a point in k-space. So let's start off. Start off with the center of k-space. And so I'll do what I was doing before, which was draw a very simple equation. So here's a simple equation. So an image, the brightness of an image at an xy point is, so remember what we first started off was the brightness of an image was just equal to the that was the very first one that we went over. So what is that? When you look at that equation, you can see y isn't present on the right. What does that mean? That means that it doesn't matter what the value of y is. Whatever you put in for y, you'll just get something dependent on x. So what we're going to do now, we're going to do a very simple thing, just add 1 to the cosine. Simplest thing we could do, and see what that does. So if you go back to the lecture on image at xy equals cosine of x only, what you got was just you got something that had sort of a dark stripe in the middle, and it looks something like this. So this was, it looks something like that. So the image was, 1, minus 1, there's minus 1, there's 1. So that's what the image looked like. It was kind of dark here, and then as you went out to the edge, it got bright. So that was our cosine brain. So now all we're doing is adding 1 to that, and then seeing what it does. So what was the Fourier transform of that guy was just 2 points. Remember, it's just 2 points in the real part of k-space, and the imaginary part was all 0. And so those 2 points were basically just at frequency 1 and frequency minus 1. Okay, so now what we're going to do is add 1 to it. And so if we add 1 to it, it pretty much looks exactly the same. I'm using light to mean dark. In the notes, this is dark. So if we look at a graph of that, we've added 1 to it. So now our cosine just goes, it's all positive. So it goes from 0 to 2. We just shifted it up 1 because, the original cosine would have started at 1 and gone down to minus 1. So all we did was we still have a cosine brain, but we just added 1 to it. So that's the real part. And here's the imaginary part, which is all 0. And we could also draw that out as amplitude and phase. And this one's a little simpler than it was last time. So now we'll just end up with 0 for phase throughout the whole thing. And the amplitude will look exactly the same. It doesn't have that sort of reversing business where we were going negative before. So that's our amplitude and phase picture. And if you just draw it out as, as vectors, complex vectors, then, we'll end up with, big arrows here, smaller arrows, and then really tiny arrow there, and then bigger, and then bigger. So the arrows won't reverse direction at all. So all that's doing is just plotting these two numbers out. Either the real and imaginary part, the amplitude and phase part, or plotted it as a vector. Okay, so now we want to take the Fourier transform of that. And consider the center of k-space. So let's just write out the Fourier transform equation. So write out the Fourier transform equation and then substitute 0 into it. So the Fourier transform equation is the 1D Fourier transform equation was that the Fourier transform at a spatial frequency equals the sum over all x of the image, that's the image, at a point in x, times e to the whole mess minus I 2 pi k, because k is frequency, and then times x instead of t. And then summed across, each point in the image. So now what we're doing is we're just saying, well, what about the center of k-space? So the center of k-space is a single point which is frequency equals 0. So there's only one of these points for two-dimensional k-space. So we have sort of x spatial frequencies and y spatial frequencies and all combinations of them, but there's only one 0 spatial frequency. And so basically if we just substitute in 0 here, just make this guy 0, what does that mean? Well, it just means we go over here and put a 0 in there. And so when you put a 0 in there, that 0 is more powerful than I. So 0 just zeroes out I. And so you just end up with e to the 0. And anything to the 0 is 1. And so the answer is this thing turns into 1. So normally this thing right here, remember, what would that be? That would normally be somewhere, somewhere around the circle pointing in some direction or other like that. So a circle of radius 1, and then there'd be some, real part and, some imaginary part somewhere around the circle. But if we substitute 0 in for k, this is just 1. So this just goes to 1, real. It's only got a real part. The imaginary part is 0. It's just a plain old 1 with no imaginary part. Because e to the 0 is just 1, and that e to the 0 doesn't have any. The result of that is no imaginary part. So that'll be 1, and so then, what does this equation boil down to? It just boils down to an average. Because what it does is, for each little chunk of the image, it multiplies it by 1, which doesn't do anything to it, and then it multiplies it by a tiny little fragment of x. It's just finding the area under the curve of this guy, and that's basically equivalent to the average value. It's equivalent to the average value. So this is basically, so this equation boils down to just the average brightness. Now when we looked at that original equation without the 1 over here, without this one, it was just, the image at xy just equals the cosine of x, look like this. We didn't mention it, but it's this guy right here. It's this one right here. So what happens if we take the average of that image going across the x direction? The average of a cosine is 0. I didn't draw it quite right, but there we go. So the average value of one cycle of a cosine is 0. And so that's why there was nothing in the center of kSpace. But now our average is not 0. Our average is going to be 1. And so what will we get when we do our Fourier transform? We'll get something in the middle of kSpace. And so there's only one frequency in here. There's only one spatial frequency in here. And so what we're going to get is we'll get 2 points for our positive and negative frequency 1. So that's frequency 1 there. But then we're also going to get a value right in the middle of kSpace. That's the center of kSpace because that represents the average brightness of the image. And it will be the average brightness across the whole image, including the y-axis. And so what will happen to the imaginary part? It'll still be 0. So here's the imaginary part of our Fourier transform. And here's the real part. And if we, think of that as amplitude and phase, it's going to look pretty much the same. So we'll have a point in the center of kSpace and then 2 points on either side to represent the single frequency that we had in there. And then this will still be 0. And if you plotted it out as a vector, you'd end up with a vector in the middle with 0 phase, and then a vector slightly off to the right with 0 phase, and a vector, so you end up with 3 points in kSpace. Now, so why is this so important? Well, if you think about it, what the average value of the image looks like very strongly affects the values at each point in the image. And one of the homework assignments will be take an image, take the Fourier transform of it, mess around with the center of kSpace, un-Fourier transform it, and see what happens to the image. And what you'll see is that the value that you have right in the center of kSpace is highly important for what the contrast of the image looks like, because you can sort of think of it as the baseline against which everything else is being compared. It has a much bigger effect on what the image looks like than any other point in kSpace. And in fact, you could invert the brightness of the gray and white matter by fiddling with the center of kSpace, just 1 point. So if you just mess around with the center of kSpace, you can make gray matter brighter than white matter, or white matter brighter than gray matter, same image that you're starting with. So very important for what the contrast of an MRI image looks like, the center of kSpace. So, and it sort of has an unreasonably large effect on the image, and so that's one reason why people pay attention to the center of the echo. The center of the echo is the center of kSpace, and so the value that you get at the center of the echo is very strongly determines what the whole rest of the image, even though there's say, for one slice there's 65,000 data points. Just that single data point at the center so strongly affects the contrast that if that one is off, you could do something like reverse the gray and the white matter. And so that's one of the reasons why we strangely pay so much attention to just the center of the echo. because what happens at the center of the echo is actually very important for what the overall image looks like. But conceptually, it's very simple. All it is the average brightness of the image. Okay, so that was the center of kSpace. So the center of kSpace, and in the very first version of looking at an image and its Fourier transform, we just left out the one, in which case the average brightness. So this guy, here. So average brightness equals 0. This is average brightness equals 1. Okay, so that's the Fourier transform of an image, what the relevance of the center of kSpace is. And you can just plug in a 0 into the Fourier transform equation, and then you can see that it's just essentially calculating the average value of the image. So what we want to do now is finally, last but not least, get to one point in kSpace, because each of our data points is a single point in kSpace. But so far, when we've tried to do as simple as possible and as we could of an image, which is just a cosine, we ended up with a minimum of 2 points in kSpace. So, like I said, I for many years I didn't fully understand what does a single point in kSpace mean. And so for a single point in kSpace, it turns out we end up with a complex image. So what is a complex image? Well, complex image is just an image that has some imaginary part. And what is the imaginary part? Well, it's not, it's just another number. It's just a second number. It's just the imaginary part of the complex number. Now, when we start off with an image, if we just take like a photograph and do a Fourier transform of it, that photograph doesn't have any imaginary parts. It just has a real value at each. It just has a real pixel value at each point. And when we do a Fourier transform of it, we take that real value and then we just substitute in 0 for all the imaginary parts. And then we can take a Fourier transform of it. When we take the Fourier transform of it, we get real and imaginary. Always get real and imaginary. And then maybe we do something, mess around in the Fourier domain, on Fourier transform it, filter it, or do something to it, and we get back a real image. And we want a real image. Our goal is to get back a real image. So why are we talking about a complex image? Well, it turns out that's what corresponds to 1 point in kSpace. And so now we're going to make a complex image. So a complex image, we can write it out as, so cosine of x, that's what we had before. But it has a complex part, so here's the complex part. So here's minus I for the complex part times sine of x. Now there's all different kinds of complex images we could have made, but we just make this very simple one here. And that one, we can also write that one out in our usual notation as, e to the minus I x. That's another way of writing that same thing out. So all this means is that it's just an image that instead of just having a real part, it's also got a complex part. So let's plot that out. So if you plot that out, so here's the real and the imaginary part of it. So you can see, you can just see the real and imaginary part right there in the equation. So the real part is just a cosine like it was before. So here's the cosine. I'm coloring in what's supposed to be dark in the notes. there's a cosine. And then now we have a negative sign. So let's draw out our cosine. So here's our positive cosine. But this guy is the negative sign. And so, a positive sign would be, like this. But we got the negative sign. So here's our negative sign. And so what's that going to be? That's just going to be, it looks like a cosine. It's just, the bump is just shifted over here. Okay, so that's our real and imaginary part of our complex image. So like a normal brain image would just have the real part, but now we're just making one up. We're just making up a complex image that has an imaginary part. So that's the real and imaginary part. But when we go to we kind of got something that's slightly weird when we go over to the amplitude. So what about the amplitude and the phase? Okay, now things get weird. It's completely flat. And why is that? Well, we know, like this simple complex number like this, a very simple complex number, is in fact an amplitude of 1. It's always an amplitude of 1. It'll just be, an amplitude of 1. It'll be a vector, pointing in some direction, and it's got a real part and an imaginary part. But the length of it is always 1. The length of that vector is always 1. That's the amplitude here when we convert this thing. So if we sort of mix a real sine and a real cosine and imaginary sine together, we just get 1. So there's nothing in here. It's just like completely uniform color across the image. There's no structure to it at all. And then if we look at the phase of it, the phase angle, so that would be like this phase angle here. What is that phase angle? Well, the phase angle, so this guy is going to be completely flat at 1, okay? So it'll be 1 across the whole image. And it's going to be, let me just write that up a little higher here. So it's going to be 0, 1. So that's 1 across the whole image. Then what about the phase? Well, the phase is going to just slowly go down until we get to, minus 2 pi, minus 360. And you can just figure that out from a sine. And if you just stick a sine and a cosine in for the x and the y component, figure out what the phase angle is, it just wraps around the clock. So it just, it starts here and just goes all the way around like that. Or the other way. Yeah, so it just wraps all the way down to, so that would look like a ramp, just a ramp like that. But now the critical thing, what does it actually look like in terms of the arrows, which sort of is a little bit more intuitive, to me at least. So what it looks like is, here's starting at 0, at x equals 0. So at x equals 0, if you work through this, the cosine's going to be 1 and the sine's going to be 0. And so that will zero out this imaginary part. So you'll end up just along the x-axis. And then you'll start rotating downward in a negative angle direction because of the minus sign. And then, so then we'll rotate around further. In the middle of the image we'll be there. And then we'll rotate up. And then rotate that way, and then rotate back. And so that will occur across all the different y points in the image. So, and again, I'm not adding any information here. All we're doing is just plotting out the 3 different ways of plotting out the real and imaginary part of these things up here. So we can either plot it out as real, imaginary, amplitude and phase, or just vectors. So now here's the vectors. So this, across the whole image. So that's actually what you get. You get this wrapping of the vectors across the image. So that's our complex image that we're starting. We just made it up. We made it up for a particular point for a particular reason, because we want to get a one point in kSpace. Okay, so now we do the Fourier transform of that. And what do we get? So finally, ft of complex image. So when we look at the Fourier transform of this, we finally get a point in kSpace. So here's our Fourier transform of it. And so what does it look like? It just looks like, honest to God, 1 point. And since the average of this, the center of kSpace is still all 0, you get nothing in the center of kSpace. So you basically just, and so that's the real part, and the imaginary part is going to be 0. So literally we just have 1 point in kSpace in the real part of kSpace. And so what does that equal if we do amplitude and phase? We'll have, 0 again, and we'll have that same point, because it's a real only. So here's a case where we have no imaginary part in kSpace, but it's a point where we only have 1 point in kSpace. So normally we would have had another point over here. There's the missing point. And that goes back to what I was sort of talking about earlier. When you just have a single point that you're correlating sines and cosines with, both sines and cosines will correlate with it. Depends on where the point is. If you put the point sort of further into a higher frequency part of kSpace, you would get more stripes over here, but you would have both cosine stripes and sine stripes. So we're right at spatial frequency 1. And so at spatial frequency 1, we just get 1 stripe of cosine and then 1 stripe of sine. Well, we get both of them when we don't have that other point in kSpace to essentially just pick out just the cosine or the sine. So that's actually 1 point in kSpace, amazingly. So what does it correspond to? It corresponds to a complex image. It corresponds to an image that has an imaginary part to it. So that's kind of troublesome. So every single data point that we collect corresponds to one of these complex images. Just to complete it, we could just draw this out. There'd just be like one vector right there at spatial frequency 1, and the angle of it would be 0, because the phase angle is 0. Here's the phase angle, and here's the amplitude. Here's vect. So basically one vector turned into this whole giant array of vectors. Okay, so now several things should be sort of jiggling around in your mind. So one of them is, if we want to end up with a real brane, and each point in kSpace corresponds to both real and imaginary in the image domain, then what's going on? And what's going on is that all the imaginaries cancel out. So if we'll explain what you need for all the imaginaries to cancel out, but if you have a particular setup of your kSpace, which we'll explain in a little bit, the end result is, even though each point in kSpace corresponds to a complex image, when we do the inverse Fourier transform, what happens is all those imaginary parts of the image all add up to exactly 0. So, what does that mean? Well, it means, like, say here's the real image vector, Because remember, we always have a vector here in our image. If it points away from the 0 axis, then it's got an imaginary part. So here's our real image vector. But how are we getting that? Well, we're getting that by adding up a whole bunch of vectors that might have imaginary components to them. But because of the special property of kSpace, we cancel them all out. So this is that's the imaginary direction, and this is the real direction. And so basically, this is what we want. We want a setup where all the imaginary parts of the image, which, since the Fourier transform, or the inverse Fourier transform, is basically a sum of a bunch of complex numbers. So when we sum up all these complex numbers to do the inverse Fourier transform, magically all the imaginary parts cancel out. And so what is the property of the particular distribution in kSpace that makes it guaranteed that the imaginary parts will cancel out and we'll end up with a real image? And so it turns out that's called Hermitian, like hermit, but it was after a French guy. Hermitian symmetry to kSpace. So it's a particular kind of symmetrical kSpace that is desirable. And so what is Hermitian symmetry? So Hermitian symmetry is symmetry when the complex conjugate, and if you're like me, it's like, uh-oh, I don't know what that means. So we have to stop. So we'll stop for a while. So what is the complex conjugate? So the complex conjugate is a very simple concept. It just means a complex number. So it's the conjugate means that it's compared to another number. So if we just take an example of a complex number like 3 plus 4i. So that's a complex number. That would be like, 3 on the real axis plus 4 on this axis. So that's a complex number right there. So 3 plus 4i. So what is the complex conjugate of that number? So that's our starting number, Cm complex num. And this is, complex conjugate of. So there's complex number, complex. It's just basically 3 minus 4i. So just reverse the sign on the imaginary part. So what does that mean? So here's the complex conjugate like that. So we've drawn it before. So it just means take a complex number and just make the imaginary part of it negative. So if the imaginary part of it was negative, you would make it positive. If it was positive, make it negative. So Hermitian symmetry to kSpace is when the complex conjugate, so now we have that. So when the complex conjugate is equal to value of function, our Fourier transform function with negative argument. So in 1D, that would mean, so here's a 1D example. We're in 2D, but we'll start with 1D. So in 1D, what does that mean? That means that the Fourier transform of negative k, that's this negative argument, equals the complex conjugate of the Fourier transform of k. So for better, for worse, there's many different ways of writing out the complex conjugate, which is quite irritating, but that's an example. This is one example. So complex conjugate, that's what that means. So let's sort of unpack what this means. So what this says is, if we take the value of the Fourier transform at k, and then complex conjugatize it, okay, by essentially making its imaginary part negative, then that will equal the Fourier transform of negative k. So that's the picture. So let's draw it out in 2D and then just draw a graph. It's very intuitive graphically once we see it graphically. So if we do it in 2D, it would be the Fourier transform of, so whatever the value of the Fourier transform at minus kx minus ky is going to be equal to the complex conjugate of kx ky. So what does that mean in actual sort of Fourier space, k space? So what that means is, if we've got our Fourier transform here, so there's the center of k space, and this is the kx direction, and this is the ky direction. Let's just take a particular kx and ky, so let's go out here, so that's kx, and say this is ky. So here's a particular ky and kx. So that would be like h, that would be h without the star, kx, ky. Okay, so what is that going to be? That's going to be, there'll be a number there. There'll be like, a real imaginary component at that number. And so to make this Hermitian symmetry work, what we do is we go to the part of k space that has negative kx, negative ky, and what does that correspond to? That corresponds to this point over here. So it corresponds to that point over there. So we go to that point over there, and then what do? Its value should be whatever that guy was real, and then minus y. So there you have it. So what does that mean? Well, it means that there's this redundancy to the k-space data, because this has to apply across the whole space. So that means like this point over here has to equal this point with its imaginary part made negative, and this point up here has to equal that point down there with its imaginary point made negative, and this point over here has to equal that point. So this has to be the negative imaginary same real as this one. So when you look at that, you can see that you can actually predict. You only need half of k-space, because you can predict the other half from it, because it's symmetrical. So why do we care about this? Okay, so why do we care about this? We care about this because if k-space is like this, so this was number one, so that's Hermitian symmetry, but our use for it is that if k-space is like that, we get a real image. That was one, and so here's two. So if k-space real only image. And so that's what we want. So we always want the value at these symmetric points in k-space to always be complex conjugates, which just means that the imaginary part is the opposite. And you could sort of see why that gives you a real image. If the imaginary part is always opposite, it's always going to subtract out, because it's always going to be the negative of this guy. And so when you add the whole mess up in the Fourier sum, they'll all cancel out. So, and we could see that in the one I just erased, here we had a Fourier transform that just had one point in it, and that one was not Hermitian symmetry, because when we went to the equivalent point in the negative part of k-space, there was a 0 there. And so that wasn't equal to the same number that we had on the other side with the imaginary part made negative. It was just we ended up with like real and 0, and then over here we just had 0, whereas it should have been, real and negative 0. So that's the bottom line. So if we have this kind of structure to k-space, then we're guaranteed that the imaginary parts of the image will all cancel out, and we'll end up with just a real image, is what we really want. Now, in spite of the fact that each data point that we collect will effectively be, it'll have an imaginary component, because it'll have all these imaginary parts. So we're essentially summing up a bunch of imaginary images, but they're magically canceling out all their imaginary parts because we have this kind of symmetry. So is real data like this? And the answer is, real MRI, k-space data like this? And the answer is no, it's very rarely like that, exactly. And so that's the explanation for when we're doing an inverse Fourier transform, we always look at the amplitude image. And so we always look at the amplitude image because the phase, if the phase isn't 0, there'll be some imaginary part. If there's some imaginary part, the phase won't be 0. And so if we just look at the amplitude, we can sort of throw away all those little phase mistakes. So that's we've reached the total bottom. The total bottom in the course was 1 point in k-space, and so it's just torturous just getting to 1 point in k-space. But this is actually 1 point in k-space. So a single point in k-space corresponds to a complex valued image. In spite of the fact that what we want to do is really sort of add up all these complex, in our Fourier integral sum, we want to add up all these complex things, but with the hope of canceling out all the imaginary parts. And in order for that to happen, you have to have this weird kind of symmetry where this k-space is kind of like the different quadrants of k-space are like mirror images of each other, with this complex conjugate business going on. If everything was perfect in our MRI data, it would look like that. But this is, only in a perfect world, and we don't live in the perfect world. We live in sort of like an imperfect world, and so we generally don't get that. And so that's why we take the amplitude image. Okay, so there's got to be some questions from this nightmare. So David will end the recording there and see if we can get a few questions.